Hi everyone, I'm Lorenzo Chelini, a PhD student from TU Eindhoven. And today in the next 20 minutes, I will try to convince you on our research on multi-level tactics, a framework for abstraction raising in multi-level IR. This is a work of multiple people, Andi from INRIA, Alex, Albert, and Nicolas from Google, Henk from TU Eindhoven, and Tobias from the University of Edinburgh. So I will start by giving a quick recap on what is MLIR. MLIR is a toolkit for representing and transforming code. It is modular and extensible, so you can plug in new dialect, which essentially are namespace of operation type and attribute, and is non-opinionated, so you could choose the level of abstraction that is right for your application. For more details on MLIR, please see previous talk given by Alex on MLIR scaling component abstraction for domain-specific computation. For the purpose of this talk, it is important to understand progressive lowering, which is the main mechanism that MLIR used to lower high level of abstraction to low level one. So this is an example. We started from an operation that belongs to an high level dialect, linalg.matmul, and progressive lowering lowered this matmul to affine, to a triple nested loop represented in the affine dialect, which in turn can get lower to SCF, so a triple nested loop in SCF, which stands for structural control flow, and in turn SCF can get lower even further to LLVM-IR. So progressive lowering has limitation in the sense that it works in a single direction, so you can just lower from high level of abstraction to low level one, but you cannot go in the opposite direction. And this also means that the entry point in the lowering pipeline defines your level of abstraction. So if some language, let's say C or C++ or any other general purpose language, enter the lowering pipeline at a pretty low level, you cannot just exploit domain-specific optimization that are available at higher level of abstraction. So in this paper, we explore the other side of the mountain, and we provide a mechanism infrastructure to raise the level of abstraction starting from low level representation. And we call this strategy progressive raising, which is the complementary of the progressive lowering exposed by MLIR. So this is a picture that shows the current available dialect in MLIR, at least some of them. At high level of abstraction, we have linalg and BLAS, and then stencil. At the middle level of abstraction, we have affine and F18, and then at the lower level, we have SCF, standard, and LLVM-IR. Here, the gray bubble represented the different entry point that you have in the MLIR lowering pipeline, which are represented by the black arrow. And in this case, if you have a rich, semantically rich language like tensor comprehension, you can use tcall to enter linalg. If you come from a general purpose language like C or C++, you can use MET to enter affine, or if you are dealing with Fortran, there is the Fortran frontend that allows you to enter F18. So in this paper, we focus on three raising paths. So we first one where we raise within affine. So we take a loop nest and raise these loop nests to an high level operation available in affine. So in this case, there is a matmul operation, which then gets lower to I optimized code following the Bliss optimization. Then the other raising path we allow using our framework is from affine to linalg. And then we have a third example where we perform a more progressive raising by lifting first from affine to linalg, and then at linalg we do an additional raising to understand to reorder chain of matrix multiplication. So what does it mean raising? This is a really simple example. So on the left, you have a code that belongs to the affine dialect, which is a low level of abstraction dialect. And on the right, you have the same code raised to high level abstraction dialect. Specifically, the top one is raised to the BLAS dialect, and the bottom one is raised to the linalg dialect, so linalg.matmul. So in order to perform abstraction raising, we do abstraction raising in 3 steps. So the first step is to understand the structure of your code. So in this case, if you want to detect this matrix multiplication, you need to first detect a three-nested loop. Then we also look at the computation and access pattern. So for gem, we need to have an addition, a multiplication. We need to have 3 load to different array and 1 store to an array C. And also we need to satisfy the access pattern typical of gem, which is IK, KJ. So once you have detect both the structure, the computation, and the access pattern, you can actually, you need some infrastructure, which we call builder, to raise the level of abstraction. So to go from matrix multiplication expressed as a three-nested loop as to an high-level operation, let's say linalg.matmul. So for the first, to detect the structure of the code, of low-level code, we provide the structural matchers, which essentially replicate the nested structure of the code, of the expected code. So in this case, we go and detect a three-nested loop. And in the innermost loop, we have a body, which is a callback that will check the access pattern. The access pattern are checked using access matchers. And in this case, we introduce a placeholder for induction variable and array placeholder for array. The matching for the access matcher starts from the last operation of the block, so the store. So in this case, we require to have a final store operation to a two-dimensional tensor with placeholder underscore I underscore j, and then we work backward. So in this case, we require to have a 3 load operation to 3 different tensor A, B, and C with different access pattern that satisfy the gem access pattern. So IJ, IK, KJ. And then we also check the computation that we have in this block. So we require to have an add operation which take in input the result of a mul operation. So once we have matched, we can use the builder to raise the level of abstraction. So for builders, I don't want to go into detail, and here I show just the generated code, but you can find more details on the paper. So we have 2 kinds of builders. We have the declarative linalg builders that allow you to create a linalg operation, and we have the BLAS builder that allow you to call a function call that belongs to a vendor optimized library like MKL. So once we have developed these matchers and builders, we understood that these are a little bit of tedious, and we don't want to expose them to the user. So we want to provide a more compact way to express matchers and builders. And we propose a solution based on table gen combined with tensor comprehension notation. This led us to the development of TDS, so which stands for Tactics Description Specification, which allow to automatically instantiate matchers and builders starting from a specification, which consists of 2 fields, the pattern and the builder. The pattern essentially represents the code that you want to locate using using tensor comprehension notation, and the builder represents how you want to rewrite the detected pattern. So in this case, is a trivial case where we want to detect a gem and lift the gem to a linalg matmul operation or a function call to a BLAS library. So to give you a little bit more interesting example, let's see how we can optimize contraction following the TTGT scheme, which stands for transpose, transpose, gem, transpose. The idea behind TTGT is to first flatten the tensor to matrix, then perform the contraction using a gem operation, and then flatten back the output matrix to tensor. So consider the following example. So the first step to in the TTGT transformation is to transpose the dimension of A and B. In this case, we want to bring M1 as outermost dimension, followed by K1 and K2, and we want to do the same for B, bringing K1 as outermost dimension, followed by K2 and N1. But then what we want to do is to collapse the 2 dimension for A, in specifically K1 and K2, and we want to do the same for B. And then at this point, we can execute this contraction using a gem operation. In In this case, there is no unflatten operation because the output is already a matrix. So TTGT can be implemented in TDS in the following way. So we first have a permutation builder that takes input the array A and output a new array D, and we reshape the dimension of A following the given expression. So in this case, we bring as outermost the first dimension, then as a first dimension the zero dimension, the old zero dimension, and then as innermost dimension the outermost dimension of the previous array. So we do the same for B. So in this case, we have another permutation builder that take B as input and output F, and with another affine expression that define the permutation. And then we have a reshape builder that takes D and output G, collapsing the first and the second dimension for D. So thus giving us a matrix. And then we do the same for F, which output H, again collapsing the zero in the first dimension for F. At this point, we can just emit a matmul builder, which take G and H as input and output C. So if you raise this code to a BLAS, what you get is a sequence of function call to MKL. So we have the two transpose call for A and B, and then we have the reshape for D and F, and then we have the matmul operation. So TDS is a little bit questionable syntax-wise because it's mixing two DSL, one that we build on top of TableGen, the one for builders, and the tensor comprehension. So we didn't want to expose TDS to the user, but and basically this brings us to the development of our third piece, which is TDL, Tactics Description Language, which allow to easily specify both the pattern and the builder only using tensor comprehension notation. So this is the definition that you need to write, that the user need to write to specify the TTGT transformation for the following contraction. So again, here you have three builders. The first builder creates the matrix G by first transposing and reshaping the contraction A. We do the same for H, but starting from the B contraction, and then we perform a matrix multiplication. So this TDL then get lower to the TDS, which is our TableGen based implementation, and then the TableGen get lower to access matchers and builders. So these are more examples for TDL. A more in-depth description can be found in the paper. Here I will just present you a couple of them. So the first TDS entry is the most trivial one. So in this case, we want to detect a pattern, which is a gem, and the builder is equal to the pattern. So meaning that we want to detect gem expressed as a nested loop, and we want to raise this gem to an high-level gem operation. So let's say linag.matmul. Of course, we can detect transposition. So in this case, B is transpose. We can directly emit a gem operation for a contraction if this is a trivial collapsing of two dimension. We can implement TTGT, and again we can avoid emitting a reshape operation if it's a trivial contraction of two dimension, and we can also handle batch dimension. So the overall flow in what we develop is the following one. So we start from TDL, the tactic description language, which get lower to the tactic description specification, which is our TableGen based implementation, which get interpreted by a multi-level tactics backend. And from this TDS, we generate matchers, access matchers, structure matchers, and builder. These matches will then get greedily applied using MLIR pattern rewriter. We get the input code starting from a general purpose language like C. We send this code to MET, which allow us to enter MLIR at the affine level. And then on the code at the affine level, we apply our matchers, and what you will get is a lifted IR that can belong to BLAS or linag. So this is essentially the three-step you need, the three-step of our flow. Again, TDL, then lower to TDS and TDS lower to mattress and builder. So I want to show you some result. So on the x-axis, you have here the different benchmark we consider, mainly taken from polybench and the contraction and also convolution. And on the y-axis, you have the gigaflops per second, and the theoretical peak of the machine is 63.6, which we obtained by running an SGEM from MKL. So here we first compare Pluto default with MLT Linarg, because they are comparable performance-wise, optimization-wise. So in both cases, we apply a tiling optimization with a tile factor of 32. Of course, MLT Linarg is expected to get better and better performance and as time goes on. But back then, essentially the only optimization we would have available was tiling. So we implement tiling, and we can already see as that MLT Linarg is already quite comparable to Pluto default. And I just want to mention that MLT Linarg is essentially our code lifted to Linarg starting from a fine. So in this case, again, I was saying that MLT Linarg can get quite performance compared to Pluto default, and mainly because on the contraction, we can get better performance than to TTGT. Then we compare Pluto Best with MLT Plus. Pluto Best is an auto-tuning that we is the best performance version of Pluto following an auto-tuning strategy where we change the fusion strategy and the tile size for Pluto. And MLT Plus is the code raised from a fine to Plus and then emitting a Plus function call to MKL. So as you can see, MLT Plus is the best performing one of the three. And I mean, the takeaway of this slide is that if we allow abstraction raising on general purpose code, we can get good performance. As a third example of our paper, we also show a more progressive raising, and we show this progressive raising considering the matrix chain multiplication. So suppose you want to compute the product of three matrices. Since the operation is commutative, you can decide the order you want. Of course, one order is better than the other. So assuming that you first start by multiplying A2 times A3, you get 25,000 scalar multiplication, and then you multiply by A1, and you get additionally 50,000 multiplication. So overall, you get 75,000 scalar multiplication. If you rearrange the computation by first performing A1 times A2, and then times A3, you get a reduction of 10 times in the scalar multiplication, which will be reflected in better performance. So we do this progressive raising using the matrix chain multiplication. So we start from a fine code, we raise the fine code to Linarg, and then at Linarg we perform an additional raising step, which allow us to apply this, to find this, optimal reordering. And performance-wise, you can see the difference. So for a matrix multiplication of 4, you can get a speed up to 6 compared to the naive code, which is basically the 3 matrix multiplication lower with clang minus O3. So I present you multi-level tactics, which is a framework for abstraction raising that allow to enable to higher level of abstraction such that we can reuse already existing domain-specific optimization for general purpose code. It consists of a TDL language that get lower to a TDS, static description specification language, and then and this TDS then get lower to access matches, structural matches, and builder. I show you also that performance-wise, we can get quite good performance. And I also show a third case where we have a more progressive raising, where we lift from a fine to Linarg, and on top of Linarg, we do an additional raising to reorder the chain of matrix multiplication. So thank you for listening, and yeah, I'm happy to take any question.